So I'm going to talk about maximum likelihood estimation and uncertainty quantification properties of Gaussian processes when the scale parameter of the covariance kernel is selected using maximum likelihood. And this is a joint work currently only on arXiv with George, Philip, Chris, and Simo. And this was mostly done at Aalto, but submitted when I had started at Turing. So our setting is as follows. So we have some set omega, which is always assumed to be sufficiently regular and bounded, and we wish to approximate a deterministic function f, which has been evaluated at some set of capital N points. So we wish to approximate this function at a point x at which we haven't yet evaluated it. And to do this, we use Gaussian processes. So we model f as a Gaussian process FGP, which is here zero mean and has a positive definite covariance kernel K. Then we condition this GP on our set of data, which consists of evaluations of this function at our data points. And then we get some GP posterior process. And this posterior has well-known conditional mean and conditional covariance functions S and P. And the conditional mean function is supposed to give us an approximation to the function f at points not yet seen, while the conditional standard deviation square root of p is supposed to somehow reflect our uncertainty about this approximation. And I should emphasize that everywhere in this talk and in the paper, this function f is deterministic and fixed. It's never assumed to be, say, a sample from the GP or anything like that. It's always deterministic. And we typically also assume that these points are deterministic. So that there's no, like, nothing is truly random here, not f nor the points. So only randomness comes from the fact that we use GP modeling. So the motivation for this mainly comes from, of course, from probabilistic numerics, where this kind of setting and modeling often appears. And in particular, there's this paper by Jagade Sarvan Ratinaval and Fred Hickenell, where they use GPs to compute integrals by modeling the integrand as a Gaussian process. And what they do there is they use the integral of the conditional variance to determine when to stop adding new evaluation points. So they set some tolerance level, and when the standard deviation of this GP integral becomes less than the tolerance, they stop adding new points and say that, okay, now we have a sufficiently good approximation to the integral. And this, of course, whether or not this procedure is successful completely depends on how well this GP conditional variance actually quantifies our error in our approximation. And then, well, GP is just a stochastic process, so it's a function for each element of the probability space. The realization from the GP is just a function defined on this set omega. And we always assume that the GP is zero mean, but that isn't our real restriction. And then this kernel K determines the covariance structure of the GP. So the covariance between the GP at two different points is given by the kernel. So this is what samples from a bunch of different Gaussian processes look like. So if we have this very smooth Gaussian kernel, then the samples are very smooth, so that the GP modeling encodes an assumption about smoothness of the function. If the kernel is rough, so modern here, then the samples are not that many times differentiable, and so on. And what doing GP regression looks like is this. So here we have a true function, which is this a black dashed line, and then we have a GP prior. So we have this. We haven't evaluated the function anywhere, so we have just a bunch of GP samples going on there, and credible interval. And then we start evaluate the function at a bunch of points, and then we get a conditional mean, which is this blue line, which goes through our evaluation points, and then we get some uncertainty at points where we haven't yet evaluated the function. And all the samples of this posterior process now go via these evaluation points or data points. So we want to use this conditional variance to quantify the uncertainty in this approximation of f by the conditional mean. But as we see here, and well, so under the GP model, we have this standard equation or standard probability for these credible intervals, where this psi a comes from the inverse CDF of the Gaussian distribution. And so when we divide both sides in this equation 1 by the standard deviation, we get that FGP minus the mean divided by the standard deviation should be less than or equal to some constant. And what this means is that for our particular deterministic f, which doesn't have to have anything to do with the actual GP that we're that we use in modeling, we would hope that this ratio here remains approximately constant when we increase the number of points. But unfortunately, when we look at this equation for this conditional variance, we see that it doesn't depend on the data, which is not that good, because that means that we have similar isolated quantification properties for two completely different functions, which is not realistic. So the standard way to induce dependency on the data in this setting is to use a parameterized kernel. So we say that, okay, our kernel is actually the original kernel times some scaling sigma. And we select this scaling using maximum likelihood, which is, I think, the most common method here. And there's a standard equation for this, and from this standard equation, it can be computed that the maximum likelihood estimate is given by this kind of a quadratic form, where we have a vector of function evaluations and inverse of the kernel mean, inverse of the kernel matrix. And now when we use this selection of the scale parameter in this equation 1, our model gives credible intervals that depend on our function and on our data. So what we want to do is we want to analyze this ratio in equation 3, so this C, which is the ratio between the true approximation error by the conditional mean at point x and the conditional standard deviation when the scale parameter of the kernel is selected using a maximum likelihood. And if this ratio goes to infinity as we increase the number of points, then we say that the model is asymptotically overconfident, because this means that the denominator, the standard deviation, decays faster than the true approximation error. So our credible intervals decay faster than the error, which means that at some point the true function value is not contained within any fixed credible interval. And conversely, if this ratio in equation 3 goes to 0, then we say that we are asymptotically underconfident. And the main result we have here is that for a number of different kernels and fixed functions f coming from different function spaces, we showed that up to certain logarithmic factors, this ratio can grow at most with a square root rate as the number of points increases. If our points are selected so that they They are space filling in certain sense. And we interpret this as saying that the GP model cannot become overconfident too fast. So there's some fundamental upper bound on how fast we can become overconfident. Of course, this doesn't mean that the model always becomes overconfident. It just says that it cannot become overconfident too fast if it becomes overconfident. And so what this looks like in practice is this. So here we have again some fixed function, this dashed gray line, and we start forming a GP posterior. So we evaluate our function at some point here. Then we have a lot of uncertainty elsewhere. Then we add more points, and so that the uncertainty decreases. And then we'd hope that the function values and, for example, the integral of the function are contained within some fixed credible interval, which seems to be the case here, which might be because the function is very smooth or something, or it's just by chance. So everything here is based on a simple expression of the MLE of the scale parameter in terms of the reproducing kernel Hilbert space norm of the conditional mean. So any continuous positively definite kernel induces a unique RKHS, which is a Hilbert space of continuous functions. And it is quite easy to see that this MLE of the scale parameter, which has this linear algebraic form, can be actually expressed as the RKHS norm of the conditional mean function divided by square root of n. And there are a lot of results in the scattered data approximation literature about how this RKHS norm of the conditional mean, or kernel interpolant as they would say, behaves for different functions and different kernels. So we basically extend and exploit those results here. And well, our first result is very general in the sense that we can take any kernel, and if our target function happens to be a member of this RKHS, then it's quite easy to show that this maximum likelihood estimate behaves asymptotically as 1 over n square root. So this asymptotic notation means here means that there's that there are upper and lower bounds, or that this quantity on the left hand side is of exact order n minus 1/2 up to some constants. And furthermore, it's easily shown that this ratio, which tells us how well our uncertainty quantification is doing, that this ratio is O(n) square root. So we get this result that we can only become overconfident slowly, if overconfidence happens. Because it can be shown that there are subsets of the RKHF in which we actually have underconfidence. So if we define this integral operator T by integrating the kernel, this is the standard integral operator you see, say, in Mercer's theorem. Then the range of this integral operator, so the function space of functions, or the image of L2 under this integral operator is a subset of the RKHS, and this is a subset of the RKHS which contains, in a certain sense, quite smooth functions. So there's an informal result saying that if all the functions in the RKHS have smoothness alpha, so say if they have alpha weak derivatives, then this image of this integral operator consists of functions having 2 alpha weak derivatives. So it's has twice the smoothness. And now if we assume that our function is a member of this range of this integral operator, then the result here, this uncertainty quantification result, can be improved in that in addition to this n square root term, we have an integral of the posterior variance. And typically, if your points cover the domain well, the integral of the posterior variance decays much faster than n2 minus 1/2, which means that usually in functions in this subset of the RKHS, the GP model becomes asymptotically underconfident, which is probably better than becoming overconfident. And so, but it's a well-known result that the RKHS does not contain the sample paths of the GP. So, which means that in some sense, the using GP to model a function in the RKHS of the kernel is somehow probabilistically misspecified. So the model, our probabilistic model, does not match, or the function we're modeling does not come from the class of functions that the model should be expected to do well with. So in this setting, we can use Sobolev spaces. So Sobolev space of smoothness alpha can be defined in this way via Fourier transforms. This basically means that an alternative definition is to say that this is a space of all functions with weak derivatives up to order L, such that these weak derivatives are in L2. And we also have something we like to call a Sobolev slice, which consists of functions whose Fourier transforms have this very exact rate of decay. So the Fourier transforms decay exactly with this certain algebraic rate. Whereas when you look at Sobolev spaces, the Fourier transforms can decay arbitrarily fast. So for example, if we take the classical modern kernel with smoothness parameter nu, then it is known that the RKHS of this kernel is up to equivalent Hilbert space norms, the same as the Sobolev space with smoothness nu plus d over 2. And so there's a fairly standard result which says that if the RKHF is norm equivalent to Sobolev space with smoothness alpha, so basically the functions in this RKHS have smoothness, at least smoothness alpha, then almost surely the samples from the GP are elements of a Sobolev space of smoothness beta less than alpha minus d over 2, which means that approximately the samples from the GP have d over 2 less smoothness than the elements of the RKHS. And furthermore, we can kind of squeeze all the samples from the GP arbitrarily close to this Sobolev space of smoothness alpha minus d over 2. And here's a simple illustration of what is happening here. So all of these spaces are subsets of the space of continuous functions. Then we have this space of functions of smoothness alpha minus d over 2 minus epsilon, which contains all the samples. This is the superset of the functions of smoothness alpha minus d over 2, which does not contain the samples anymore. And then we have this slice S alpha minus d over 2, which is kind of precisely where the samples are. So we cannot actually show that this S is somehow the best or smallest space containing the samples, but this seems to be somewhat intuitive, and our results on on the maximum likelihood estimates confirm this intuition. So if we assume that our function lives in this Sobolev slice, and this Sobolev slice has smoothness which is less than the smoothness of the RKHS. So we have the smoothness of the RKHS is alpha, and the smoothness of the function is beta. And under some assumptions, all of which are not actually listed here, we can show that up to certain logarithmic factors, the maximum likelihood estimate is asymptotically of this order. So it depends on the difference between the smoothness of the RKHS and the function. So if the function is much less smooth than the RKHS, then the maximum likelihood estimate will explode with some polynomial rate. But regardless of the difference in smoothness of f and the RKHS, we can still show that this ratio of quantifying the uncertainty, or telling something about the uncertainty quantification properties of the GP model, is still O square root of n up to some logarithmic factors. Now, in particular, if f is in this Sobolev slice, which approximately corresponds to f being kind of like a sample from the GP, is not a special case here. In the sense of the uncertainty quantification properties, we still have this same result that we have at most square root cross. However, it happens that the maximum likelihood estimate is up to logarithmic factors, again, a constant, which somehow confirms the intuition that this S space is probably somehow containing all the samples from the GP. And here are some simple numerical results about this. So first we have, in this example, we have a function which is in one of these fixed Sobolev slices, and we take kernels that induce Sobolev spaces with different smoothnesses. So we vary the smoothness of the kernel, and we see how the maximum likelihood estimate behaves. So based on the theory, we would expect that the MLE is asymptotically n to r, where r depends on the smoothness of the kernel. And here the dashed lines are the theoretical predictions, and the gray lines are true values of the MLE. And we see that the theory seems to be predicting the behavior of the MLE quite well. So this weird behavior of the MLE is caused by the fact that our point sets are not quite uniform, because they are taken as being nested. But the general trends are confirmed by the results. And in the second example, we take a fixed kernel, which in this case induces a Sobolev space of smoothness 2, and then we take functions of varying smoothness. And here we plot results for integrals of f instead of point evaluations, but the results for that are not really any different. So here for example, we see that this red one corresponds to the fact that the function is much less smooth than the RKHS, so the maximum likelihood estimate explodes. And the other ones correspond to, well, the blue one corresponds to slightly less smoothness than the blue one actually corresponds to f approximately being a sample from the GP. So in that case, we see that the MLE seems to be remaining constant. And here, it's a bit difficult to interpret what this means implies for uncertainty quantification. It seems that if the function is less smooth than the RKHS, we has some slight overconfidence, but this happens very slowly. Whereas if the function is in the RKHS, we either have very little overconfidence, or then the model is actually somehow honest. So this ratio goes to a constant. So in conclusion, we have shown that the GP conditional STD can contract with at most rate n-1/2 faster than a true error, and if the function is in the RKHS. And furthermore, if we are in the setting of Sobolev spaces and the function is not necessarily in the RKHS, the same holds, but there's some extra logarithmic factor here. And now, in particular, in this case when the function smoothness of the function is a d/2 less than the smoothness of the RKHS, corresponds to f being a sample from the GP, which means that in this case there's nothing special about this case. We don't get some kind of honesty or non-overconfidence in this case. Furthermore, if the function is actually much smoother than the model is assuming, then we can show that there is asymptotic underconfidence. So if the function is in this range of this integral operator. And well, these results also hold for numerical integration. So if someone is interested in Bayesian quadrature, pretty much exactly the same results hold for that. And it needs to be kept in mind that these are not in any way tight. So it is possible that there isn't a single fixed function for which this ratio between the true error and the STD grows with square root rate. It may be that it's the rate with which it grows is always less than square root, but it's very difficult to say anything about that. Thank you.